Okay, this is the second hour of Physics 1B for October 18th, and we're going to be now talking about molecule collisions. So prior to this, we have pretty much assumed that molecules in a gas are not going to collide with one another because we assumed that they were point particles, meaning that they had pretty much no volume. But what we want to do now is to come up with a way to understand how frequently collisions occur and how far can a molecule travel before it collides with another molecule. That's ultimately what we want to prove here. Or not prove, but kind of derive, is how long in space a molecule can move, how far in space a molecule can move before colliding with another molecule. So to do that, we have this picture right here. And in this picture, what we have are different gas molecules represented by these spheres. There's five little gas molecules here. And we've got one molecule here in particular that's moving to the right with a velocity v. Presumably all the molecules are moving, but we're just looking at this one. And we're looking at the chance that it collides with another molecule here. And so if we read the caption, it says, in a time dt, a molecule with radius little r will collide with any other molecule within a cylindrical volume of radius 2r and length v dt. So the idea is that any other molecule that happens to be in this volume will feel a collision with this molecule here, okay? And there's a picture below to kind of get you to think about, well, this is thinking ahead. We'll get to this in a second. So, but 18.15, focusing just on this, this molecule in some time interval that we call dt, which is just arbitrary. It could be 10 seconds. It could be a millisecond. It could be a nanosecond. It just means a time interval. The distance that molecule travels would be vdt, and we're going to assume that it would collide with any molecule inside of a volume that has a radius of 2r, because the radius of the molecule here, if I can see this here, right here, r is only half of the volume here, because if a molecule can fit in half of the volume, then this molecule will still hit it, right? So that's why it's a radius of 2r, because then a molecule that has a diameter of 2r, right, will fit right inside of there. So we want to figure out the number of collisions per second. Okay, and we're going to define this as dn dt. Okay, so the number of collisions per second, we're going to call dn dt, which means that the total number of collisions which we're just going to call dn, should be equal to the number of molecules that actually fit into this volume. So we'll call that number of molecules per unit volume, the kind of number density, multiplied by the volume of the cylinder. Because the idea is that this molecule is going to collide with any other molecule within the cylindrical volume. So on our picture here, there's only one, right? But in principle, there could be more. There could be a lot of molecules in here. And the question is, how many molecules is this one going to collide with, okay? So to figure that out, we need to know how many molecules there are in here, the number of molecules per unit volume, and then we multiply by the volume of the cylinder. Okay? So that's going to be this. The volume of the cylinder is going to be the area of the end cap, which would be pi times 2r squared, multiplied by the length of the cylinder, which will be v dt. Hopefully everybody can see that. That's the volume of the cylinder. So this would be equal to, I'm going to divide the dt over here, because ultimately we were trying to get number of collisions per unit second. So this is going to be equal to So we've got a 4 pi r squared, it looks like, an n of v Did I leave anything out? Oh, I left something out of this. Oh, v, velocity, in the numerator. There we go. I'm trying to distinguish between the lowercase v and the uppercase v, which I do by putting these bars on the top. Okay, so does that look right? Did I drop anything? There's a 4, there's a pi, there's an r squared, there's a big N, there's a little v for velocity, there's a big V here for volume, and then we can also check to make sure that the units of this actually make sense. It should have units of number per second, which is basically just 1/seconds. Meters cubed in the numerator per second divided by meters cubed, yeah. Meter squared times meter per second will be meter cubed per second, and then we have meters cubed. So this is correct, I think. So this is the number of collisions per second now that we've calculated, d and dt. Okay. The next thing we can do is we can say that the inverse of this is going to be what's called the mean free time, okay? Mean free time means how long can something move freely, okay? This is going to be equal to 1 over dn dt. We're going to call this the mean time between collisions. And this is going to be volume divided by 4 pi r squared in v, like that. Mean free time, so that's the average time between collisions. Should we pick some numbers here to get something out of this that's reasonable? Let's do that. Let's plug some numbers in here so we can understand what's going on. Let's say we have a volume. So let's let the volume be equal to 1 liter. So that's 0.001 meter cubed, right? Number of molecules, let's just use Avogadro's number. Okay, which is, just to keep reminding you, that's 6.022 times 10 to the 23 atoms per mole. We're just going to use the atoms part of it, but anyway. So 1 mole of atoms. And let's use a velocity. Let's say we use the velocity of one of the RMS velocities that we got from earlier. Like, let's use this one. Let's use oxygen. So let's use 483. And let's throw all that stuff in here and let's get a kind of calculation for what the mean free time will be. Oh, we need a radius of a molecule. We're going to use r equal to 10 times 10 to the negative 10 meters for r. I think this is a good radius for a molecule. It probably needs to be bigger, honestly. But let's use that number and let's see what we get. Okay, we can see all the values here, so I'm not going to actually write them down into the equation. Should I? I probably should, actually. Let's do it. All right, so this would be 0.001. Can you all start calculating this as I write it on the screen? You can see that the bigger the molecule is, the less time between collisions, which I hope that makes sense. The bigger the molecule is, the less time you have between collision. Okay. And then times n, which we say we're going to use 6.022 times 10 to the 23. This also means that the more molecules you have, also, the higher the probability that there is a collision. And then we multiply by VRMS. We said we were going to use 483. You can also see then that the faster the molecules move, also the higher probability for a collision. It means less time for the collisions to occur, or less time between collisions, more collisions per second. All right, what do you get if you do this? Does it do pi like that? I think it does. What does it do? Just pi, okay. Oh, we got some answers. Thank you. Okay, I'm going to trust that 2.7 times 10 to the minus 13 is correct. 10 to the negative 2, okay, and then we got the 6.0, 23, and we got the 483. Yeah, I agree with y'all. 2.74 times 10 to the minus 13. Thank you. Scroll down a little bit. Oh, yeah. So there's this other thing that just randomly shows up. Sorry. So they also say the average... Where do they say it? The results is that only one molecule is moving. It turns out the collisions are more frequent when all the molecules move at once. And the above equation has to be multiplied by a factor of 2. I forgot about that part. Yeah, so there's supposed to be a square root of 2 on here. Thank you so much, Troy. Appreciate that. Appreciate that. So if we put the square root of 2 on there, then the other square root of 2 has to appear in the denominator down here, right? So we need a square root of 2 here. Yeah, thank you so much, Troy. I forgot about that. And basically the idea there is that it's just saying that so we end up getting 1.9 times 10 to the minus 13. I'm so glad you mentioned that. I can't remember if I actually put the... Okay, so this means that there are collisions occurring every 1.9 times 10 to the minus 13 seconds. That is extremely quickly. This, I think, is equal to 0.19 picoseconds. Picoseconds, a very short amount of time. Otherwise, the equation looks correct, right? Just to add that square root of 2 on there. Looks fine to me. 4 pi square root 2 r squared bn over volume. Yep. Okay. So, yep, that means that there's a collision occurring this often. Very, very, very frequently. Really, really, really often. Now, I mean, some of the assumptions we made here may be wrong, but you know, the only real assumption that I made was this one right here. So, you know, I guess one other thing that could reduce the mean time is if we allowed the volume to be bigger. So if you cram a bunch of molecules into a tiny volume, then they're going to have more frequent collisions. So, okay, now the next thing we can calculate is what's called the mean free path. These are all things you're going to have to calculate on a test, and they're really not hard to do as long as you just understand how to use the equation. For mean free path, the symbol that's used is lambda mean. I don't know why they use lambda. They do, though. This is going to be equal to the velocity of the molecules multiplied by the mean time. Now, the good thing about this, the mean free path, is that it's velocity independent, because if I take my equation for mean time right here and I multiply by velocity, basically the velocity just disappears, and we end up getting volume divided by 4 pi r squared n multiplied by root 2. So that's the equation for mean free path. That's also the equation I believe that Troy shared. Oh no, you didn't share this one, but this is one of the equations, okay? So mean free path is basically just how far molecules travel on average, you know, before they collide with another molecule. If we wanted to use the values that we have right here and find mean free path, all we would need to do is to take our answer and multiply by the velocity that we used, which was 483, and we get a mean free path of 9.3 times 10 to the minus 11, a really tiny number, obviously. Shouldn't be too surprising that they don't have to travel far before colliding with other molecules, though. Okay. That's less than the size of the molecule. What that means, actually, I think, is that we packed these things in so tightly that they don't even have to travel. That's really kind of funny. Anyway, probably packing them into 1 liter is too small, is what I'm thinking. I think we should have used something like 22 liters for this. Okay, now we can do a couple of other things here. Let me go back to some equations that we've learned in the past. So we have our equation PV equal to nRT, right? There's another version of this equation, of the ideal gas law, that's equivalent, which says that PV is also equal to total number of molecules in times the Boltzmann constant times temperature. This is an equation we're going to be, I think, using a little bit more in the upcoming chapters. So both of these are equivalent to each other, and the way that you can prove that they are is because if you take capital R and you divide by Avogadro's number, this is equal to the Boltzmann constant. So you can do, I guess I can just do it really quickly right here. You can do a little derivation here to prove this is true. So if you do N times Boltzmann constant is just gas constant divided by Avogadro's number times temperature, then Avogadro's number divided by, capital N divided by Avogadro's number is the same thing as number of moles. We actually used this earlier, so that's how you end up getting that this is just the same thing. N over Na is the same thing as nRT. Okay, so either one of these equations are useful for us. So it just depends on kind of what you have in the problem. You may notice in this problem, or in the definition of the mean free path, we have volume divided by number of molecules right here. So what we can do here, I'll just get rid of this. We've done that derivation like 3 or 4 times now, so I'm just going to keep doing it until you get comfortable with it. And really, you just need those relationships to get there. I just want to make sure. Yeah, this is correct, right? Yeah, it is. Okay, so here we have volume divided by number of molecules, right? So what's that equal to? Well, according to this equation here, I think there's room to write this. Volume over N, right, would be equal to pressure. It would be kBT over pressure, right? Does that look right? Yes, no. Did you all hear the question? Does this look correct to you? Yes, thank you, Miss Alpha. Okay, so if volume over N is equal to kB over T, we can also write that mean free path is equal to, this would become Boltzmann constant times temperature divided by 4 pi r squared, and then we have pressure, so we'll put root 2, and then here's the pressure down here. So this is the other version of the mean free path that you can have, which you get by using Boltzmann, or the ideal gas law equation. So I guess this would really only work for an ideal gas, basically. We could also mention that as temperature goes up, the mean free path goes up. Is that reasonable? They're saying that if the temperature is increased at constant pressure, the gas is going to expand. So if the gas expands, that means the average distance between the molecules increases. That makes sense. And then that causes lambda to increase. I think we're using a cylinder because the molecules are spherical, Troy. So the kind of space they occupy, so to speak, right, is cylindrical. Good question, though. Okay, let's do a problem. Got the two equations right here. We want to estimate the mean... Hey, look at that. The radius of two... Okay, anyway. Estimate the mean free path of a molecule of air at 27 degrees Celsius and 1 atmosphere of pressure. Model the molecules as spheres with a radius of 2 times 10 to the negative 10 meters. I don't know why that made me happy that the number I picked was approximately right, but I guess it's just based on something I learned in the past. Estimate the mean free time of an oxygen molecule with V equal to VRMS at 27 degrees Celsius and 1 atmosphere of pressure. Okay, so we're actually going to do something with an oxygen molecule, and so we're going to use the RMS of that, which we also use for what we did, but that's fine. Okay, so we have that equation right there. We're given, let's write what we're given. We have temperature equal to 27 degrees Celsius is 300 Kelvin, right? Pressure of 1 atmosphere, which is basically 1.013 times 10 to the 5 pascals if we want to use that version. We don't have to. And we're using a radius for the spheres that's equal to 2. This is getting off the screen. So we'll write it over here. Radius equal to 2 times 10 to the minus 10 meters. And we want to find the mean free path, lambda mean. It's equal to Boltzmann constant, which is 1.38. Multiplied by the temperature, 300 Kelvin, divided by R is 2 times 10 to the negative 10 squared, root 2. And now you all tell me, which one of these should I use? Should I use atmospheres or should I use pascals? Based on the other things that are going on in this problem, should I use atmospheres or pascals? Yeah, we have to use pascals, right? Because the joules right here. So we would have that. So lambda mean is so I got 5.75 times 10 to the minus 8. Meters. And we can check to see that the units are actually meters real quick. So we've got joules, which I'm just going to say for the sake of simpleness is Newton per meter, or Newton meters. Joules per Kelvin times Kelvin divided by meters squared times Pascal, which is newtons per meter squared. So cancel, 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 cancel. Just have a meter left over, which is what we want. That's good. All right. Any questions about that? Very plug and chug. You just got to know what the right equation is. So the biggest thing is, on a test, if I ask you to find mean free path, just remember that you're going to use this equation. It's obviously going to be on the test, but just because the equation's on the test doesn't mean you'll know what the right equation to use is, as I saw when I graded the exams. So, any questions? This is part A. Okay, part B. Estimate the mean free time of an oxygen molecule with V equal to VRMS at 27 degrees Celsius. So now we're going to be doing the mean free time equation, which is basically this equation divided by V. Right, it's the same equation, V over 4 pi r squared in root 2. We just divide by V. So let's just do this. We'll just copy this. This feels like cheating, at least in terms of teaching. T mean will basically be this over VRMS, which VRMS for oxygen at, we should calculate this now. We need VRMS for oxygen at 300 degrees Kelvin. The thing is, I think we already did that, right? Right here, yeah. So it's 300 Kelvin. We found that the RMS velocity was 483, so you can refer back to that. So if we plug in 483 here, then this divided by 4a3, 1.2 times 10 to the minus 10. Oh, not meters per second, this would just be seconds. And that is equal to 0.12 nanoseconds. In case you have a good understanding of nanoseconds. All right, that's that. Any questions? Still got a decent amount of time left. Okay. So, the final topic for today is heat capacities of gases. And solids too, but we're mostly going to talk about heat capacities of gases. So the question here is, what happens when you add heat to a gas? We now know that when you put energy into a gas, the kinetic energy of the gas goes up. Okay, and we know just how much the kinetic energy goes up by adding heat to a gas, all right? So we've got some tables here that we're going to refer to, and I put the actual wording of what we're doing right here because I wanted to just be really consistent as to how we get to this result. So suppose that I have a gas, right? Got my little molecules in here, they're zipping around all over the place. So we have a gas, right? And let's say that we add energy into the gas, okay? So we take some amount of energy, dq, right? And we shove it into the gas. So we heat it up, right? Basically what we're doing is we're heating the gas up. And as a result of the heat, some amount of dq is going into the gas, right? What we know now is that that's going to cause an increase. So the addition of heat which we're going to call dq, leads to an increase in the kinetic energy, right? Which we'll call dk, tr, okay? So we know that basically every one of these molecules here gets a boost to their kinetic energy, okay? Their kinetic energy is now increased by some amount positive that we're going to call dk translational, okay? And we can quantify each of these objects because we've now learned that when you add heat to a gas, we have this equation, right? dq equal to number of moles times the molar specific heat at constant volume. We're calling this CV here. It's the molar heat capacity at constant volume, CV. All right. We have this equation here. Just to remind you of that equation comes from, if we use our MCAT equation, this is the MCAT equation, or what people call the MCAT equation, dq equal to mc delta t. You can replace the mass with number of moles, which leads to replacing the specific heat with the molar heat capacity. So it's the heat capacity per mole, okay? The difference is, you can look over here at the units. I don't know how well you can see this. Let me make this a little bigger. It's not letting me select it. Here, I'll move it down just a little bit. So molar heat capacity is measured in joules per mole Kelvin. So this equation over here on the left, you probably used a version of this on your homework at some point. I don't know if you don't know it, but it's just the version of the MC delta T equation where you replace mass with number of moles and specific heat with molar heat capacity. So we derived this. You can look back in section 17.5 in the book or refer back to one of the earlier lectures where we derived this equation. Okay, regardless, when I add the heat dq, we know that there's going to be a temperature increase, right? And the temperature is going to increase according to this equation right here. This is like all the problems you did with calorimetry, right? But we also know, according to our equation that we've derived last time, that if we take the equation we had was that the total translational kinetic energy of a gas was basically 3/2 times N times R times T. But if I tell you that there's going to be an increase in this quantity, the thing that's going to change is the temperature, right? So that's why it says that that dk is equal to 3 halves nr dt, because an increase in kinetic energy corresponds to a temperature increase, right? So here's the idea. We add dq into here. It leads to a positive temperature change, which leads to this. Okay, this is kind of the pathway here. You have a heat increase, which leads to a temperature change, which leads to the energy of the molecules actually increasing. Now, all this stuff happens at the same time. It's just they're all connected to each other, right? And what we'd like to be able to do is just connect these equations to each other, which we can do. Because what we can say is that dq is the heat input needed for a temperature change dt. So if the translational kinetic energy represents the total molecular energy, as we've assumed, then dq and dk have to be equal to each other, basically. They're both energies, right? So if there's an increase in kinetic energy of these molecules, it must only be coming from the heat increase, because where else could it come from? It's not like there's anybody in here speeding the molecules up. So any increase in the energy of the molecules has to be directly related to the heat that came in. So you can equate these two equations, right? And they've done that here, but I can write it over here. So if you take 3 halves nr dt, and you set that equal to n cv dt, then everything cancels out except for 3 halves r. And we get this relationship. This relationship says that the molar heat capacity at constant volume of an ideal gas of point particles is equal to 3 halves times r. This is a pretty remarkable result because it's so simple. It's very remarkable. It tells us that there's a direct connection between the r that shows up in the ideal gas law equation and specific heat. That's really what this says. I know it says molar heat capacity. It's the same thing as specific heat. It's directly related to specific heat. So it's pretty crazy that it's that simple, actually. 3 halves r is what CV is. And when you compare it to the actual values over here, what do you get? So 3 halves r, what is that? So that's 3 halves of 8.31 joules per mole Kelvin, right? What's that equal to? Well, it should be equal to something like 12.47. Let's see. Oh, whoops, 1.5. 12 yeah, it's like 12.47. This is 12.47. And the units, of course, are just going to be also joules per mole Kelvin. But you also notice something here. This is just monatomic gases. Right? And you notice the monatomic gases, they follow what we just wrote, 3 halves r, right? But when you come to diatomic gases, okay, the numbers change, right? The diatomic gases have something like 20. And then polyatomic gases, the numbers kind of change even more. So what's going on? So the idea is, and this comes from something that's called the Equipartition Theorem, and I included this piece of text down here that I'll show you now to describe this. The idea is that the 3 that shows up right here in this equation, okay, is because for a monatomic gas, if you think about the kinetic energy of a monatomic gas, right, it's related to the velocity of the gas. And a gas molecule can move in pretty much 3 dimensions, right? It can move as in the x direction, it can move in the y direction, it can move in the z direction. So those 3 dimensions we call 3 degrees of freedom. And with those 3 degrees of freedom, we believe that the monatomic gases like helium and argon have a 3 right here. But for the diatomic gases, for all of these, CV is equal to 5 halves r. If you do 5 halves times r, what you get is, so 5 divided by 2 times r, you get about 20, which is exactly what, 20.75. 20.77 is exactly what you get for nitrogen right here. And it's pretty close to what you get for the rest of these, right? So what's going on with the diatomic molecules? Well, the diatomic molecules, here, let's go back to Physics 1a. What kind of kinetic energy did we learn about in Physics 1a? We learned about translational kinetic energy, which is 1/2 mv squared, right? What was the other kind of kinetic energy you learned about in Physics 1a? There were 2 types, right? Rotational, right? So if we're imagining that these molecules are point particles, then for the monatomic molecules, the idea of rotational energy changing is not realistic. They do have something called intrinsic spin, but it really can't be changed by adding energy. For the diatomic molecules, though, they can rotate, right? If you think about a diatomic molecule, let's say it's shaped like a bar bulb, right? Well, it can rotate like this, right? But it could also rotate, so that would be like, imagine that I put a pin through the center of the screen and it rotates around like this. But it doesn't have to rotate like that. It can also rotate this way, right? So it can either rotate around like this, right? Can you all see what I'm doing? This pen is black. I don't know if it's very good. If I hold it to the side. It can rotate like this, right? Or it can rotate this way, right? So it can rotate like that or like that, right? Which gives it an extra 2 degrees of freedom. So the rotation that way, and then the other rotation, I guess I can draw on the screen here. So one rotation would be like that, and the other rotation would be, imagine an axis going through here, and it rotates around that axis. So that adds plus 2 degrees of freedom. And the idea is that for every degree of freedom, you're going to have 1/2 R, okay? So the monatomic gases have 3 degrees of freedom because Vx, Vy, and Vz. Okay, these lead to 3 degrees of freedom. So that's why these have 5 halves. And then the polyatomic ones, I think the idea is they can vibrate as well, giving additional degrees of freedom. And I think these ones might be closer to 7 halves R. Let me check that. What is 7 halves R? 7 divided by 2 times 8.31. 29. That only really applies to these two. Looks like, what is this? Hydrogen sulfide is not quite the same. Okay, let's actually read what this says right here, because I put this on here for a reason. Put this here, and I'll pull this up as well. Okay, so let's actually read what this says, because the book kind of is skipping over something here, and I'll put this picture right here as well. Okay, so it says the principle of equipartition of energy. So this is a really important principle in what we call statistical mechanics, which is also an important principle in thermodynamics. But it can actually be derived in terms of energy, but it's not done in this textbook. So if you're interested in a derivation of this, you can look to a higher level textbook where you can probably find a pretty easy derivation on the internet. So it says the principle of equipartition of energy states that each velocity component, either linear or angular, has, on average, an associated kinetic energy per molecule of 1/2 kT. So let's take that back to the equation that we have seen before. They're actually doing it right here. So we had this equation before, right? That was 1/2 m v squared average. The average kinetic energy per molecule we said was equal to 3/2 kT, right? So what they're saying is that 3 is because each Vx, Vy, and Vz contribute 1 degree of freedom. And it's saying that, let's read it again. The principle states that each velocity component, linear or angular, has on average an associated kinetic energy per molecule of 1/2 kT, or 1/2 the product of the Boltzmann constant and the absolute temperature. The number of velocity components needed to describe the motion of a molecule completely is called the number of degrees of freedom. For a monatomic gas, there are 3 degrees of freedom for the 3 velocity components. This gives a total average kinetic energy per molecule of 3 times 1/2 kT, which is consistent with, this is equation 8.16 right here. This is equation 18.16. Okay. But what about the diatomic molecules? So here's the motions of a diatomic molecule on the side right here. There's translational motion. The molecule moves as a whole. Its velocity may be described as the x, y, and z velocity components of its center of mass. Right? So we have Vx, Vy, and Vz for the center of mass. We can treat each atom's mass as being located at its nucleus. There's also rotational motion. The molecule rotates about its center of mass. The molecule has 2 independent axes of rotation, which are the 2 that I described. I don't know if their picture's any better than mine, but what they're saying is, imagine an axis running through here we call x. It can either rotate about the y-axis, like this, or it can rotate about the z-axis, which is like this, right? It can either rotate around in a circle like this, or it can rotate around in a circle like that, basically. Okay? big circles this way, or kind of like sideways circles this way. Now, you might also say, well, can't it rotate this way? It can, right? Sure. Why can't we deal with that? I think what they say is that we're going to assume that this is the spin axis. They're really vague about this in the textbook. What do they exactly say? I think what they're implying is that the spin axis is the kind of intrinsic spin of the molecule. I want to read exactly what they say because I didn't include it here. It says, for a diatomic molecule, there are two possible axes of rotation perpendicular to each other and to the molecule's axis. We don't include rotation about the molecule's own axis because in ordinary collisions, there's no way for this rotational motion to change. There's no way for this rotational motion to change. So I think what they're saying is that, yes, it's rotating this way, but there's no way for it to change, which maybe I'm taking this too far. To me, that means that they're talking about intrinsic spin. When I say intrinsic spin, do you all know what I mean? This is something you probably, I don't know, maybe a lot of you haven't studied this. You pretty much would have had to take in chemistry, I think, or 1D. When I say intrinsic spin, do you all know what I'm talking about? No. Okay. So, like, molecules, let's take it down even farther. It's a good question of, like, how deep down the rabbit hole do I want to go here? So, you all know that a hydrogen atom, right, is composed of a positively charged nucleus, right? And it has an electron as well, right? And you know that the electron kind of rotates somehow. Yes, Astrolover, that is correct. You know that the electron has orbital motion, right? It has rotational motion, it orbits, right? Okay. So the electron has orbital angular momentum, okay. And what is that? Well, that's going to be just your normal, if I know the velocity, right, and I know the radius of this, then the orbital angular momentum would just be equal to m times v times r. It's actually not equal to this, but classically that's what we would say, right? You take momentum, you multiply by the radius, that gives you angular momentum. Does that ring a bell to you all? I know it's like angular momentum is like the thing you learn at the very end of 1A, so you might not remember it very well. Maybe your class didn't even cover it, I don't know. But angular momentum is this thing where you basically just take momentum times distance. That's it. It's basically the rotational equivalent of momentum, you know? Like, we've got rotational equivalents of everything, right? We've got linear kinetic energy, we've got rotational kinetic energy, you've got just normal translational forces, and then you've got, like, torques, which is like rotational forces, right? So with angular momentum, you have regular momentum, and then you've got angular momentum. And pretty much always how you go from the normal thing to the angular thing is you just multiply by r. It's pretty much always what you do, right? Torque is just force times r, right? So that's orbital angular momentum. But that's not the whole story. It turns out that these electrons also are spinning, okay? So we'll call this the spin axis. Spin axis. And the electrons themselves also have what's called intrinsic spin. So that's another type of angular momentum as well. So we can also say that our electron has spin angular momentum. And this type of spin, it's referred to as intrinsic spin. This spin here is the same thing as what I'm talking about as intrinsic spin. And this is because it's an intrinsic property of the electron. And it turns out that for the intrinsic spin, okay, this is the part that's really crazy, the spin angular momentum for the particle actually always comes as plus or minus h bar divided by 2. Or usually it's referred to as plus or minus 1/2 spin. We don't worry about the h bar. In fact, in a lot of unit systems, like the unit systems that I worked in, we basically set h bar equal to 1. If you don't know what h bar is equal to Planck's constant divided by 2 pi. I know I'm probably introducing a lot of ideas that maybe you may or may not have seen before. I don't know. But Planck's constant is what H is. The point is this. It turns out that there's only two possibilities for the electron spin inside of a proton, or sorry, inside of the hydrogen atom. It can either be positive 1/2 or negative 1/2. And Astro Lover is acknowledging that she has heard this before. Now that I say it this way, does spin angular momentum, intrinsic spin, electron spin, does it sound more familiar, this idea that it can either be plus or minus 1/2? Nobody's responding, so I'm gonna assume no. You can say no. It's okay to say no. Like, you can just be like, no, I have no idea what you're talking about. That's totally fine. It's totally fine. Anyway, okay, no, good. All right. So, anyway, those are the only two possibilities. It can either be spinning this way or it can be spinning this way, right? When we talk about spin, if something's rotating this way, you wrap your hands this way and you say it's spinning up, or it can spin down. So, here's the thing. You can't have two electrons, all right, in the same orbital state, that is to say with the same orbital angular momentum, and the same spin state. So if you want to put another electron into this orbit here, it cannot have positive 1/2. It has to be negative 1/2. So if I want to put two electrons inside of this one orbital here, then one of them is going to be plus 1/2 and one of them is going to be minus 1/2. Okay? And we can take this a step further. Because that rule, which is called the Pauli exclusion rule, figured out by a brilliant physicist named Wolfgang Pauli, it states that if I want to pack two electrons into the first orbit, one of them has to be spin 1/2 and one has to be spin 1/2, negative 1/2. After you've done that, which is what happens in a helium atom has its first orbital completely filled, because there's only a possibility of having one plus 1/2 and one minus 1/2 to fill its orbitals. When you get down to the second row right here, what happens is that for lithium, beryllium, boron, carbon, all of these, all the way up to neon, they have their first orbital is filled with a plus 1/2 and a minus 1/2 electron, okay? The next orbital can hold, I think it's 6 electrons, or is it 8? It's 8 electrons. Has to be 8, right? Because this is 10. And within that orbital, you have more possibilities, I believe, for the electrons, but the point is that this idea that the spin can only come in these integer multiples right here eventually leads to the way that the periodic table is constructed. So this idea of spin is really important to the development of the periodic table. All right, so to carry this back to what we're talking about, what we're saying here is that each degree of freedom contributes 1/2 kT. So if I have a diatomic molecule, we know two things. One, we know that its molar specific heat is 5/2 times R. We also know that its kinetic energy is, instead of being 3/2 kT, is going to be 5/2 kT. Those are the two things that we know that come out of this, okay? And the spin axis, I think, is connected to intrinsic spin, which can't be changed by collisions. Okay, so I think that's that, and I think we can do a problem now, right? Here's something that's interesting as well. Here's this this graph right here that we should talk about, I guess. So in this graph, what they're talking about is the value of the molar specific heat as a function of temperature. And what they're saying is that below 50 Kelvin, the value of the molar specific heat is about 3R/2, because it says the molecules undergo translation but do not rotate or vibrate. And then it says as you get above 50 Kelvin, which is still pretty cold, right? 50 Kelvin is really close to absolute zero. This appreciable rotational motion begins to occur above 50 Kelvin. So between this range here, which looks like from about 250 Kelvin up to about 2500 Kelvin, the value of CV appears to be equal to 5R/2. And then it says appreciable vibrational motions occur above 600 Kelvin. So the one other thing here that's mentioned as a degree of freedom is that the molecule could oscillate as though the nuclei were connected by a spring here, because they do have a bond, then it can vibrate. And it's saying once you get hot enough, those vibrational modes, we call them modes, come into play. And as a result, you get an additional, looks like 2 degrees of freedom, right? Because then specific heat, this thing goes to 7R/2 there. Okay. Oh, maybe that's it. Maybe I don't have a problem with this, and we're out of time, so that's good. If you haven't heard of this before, if you haven't heard of electron spin, I would highly recommend going and reading about it. And specifically, this is what I would read about. The Pauli exclusion rule. Because this literally is the explanation of where the periodic table comes from. Technically, historically, the periodic table was discovered by Mendeleev, or that's who we give credit to. And he just kind of like figured out the patterns, but Pauli figured out that there's actually something quantum mechanically that's happening with electrons and electron orbitals that constructs the order of the periodic table. So just something to read about. All right, that concludes, I think, Chapter 18. You should be able to do all the homework stuff now. Next week, we will start with Chapter 19. I'm just going to remind you, as I said at the beginning of class, you need to read F2 before you come to lab on Wednesday. So that goes for all of you. You should all start reading it now, because it's long. It's going to take you at least 2 hours to read. You need to read the entire thing before you come to lab, okay? If you do that, the lab probably won't take very long, but if you don't, then you might not be able to finish in time, okay? Any questions about anything before we stop today? I keep forgetting about that. I'm glad you said that. Yeah, I'll try to do that today. I keep forgetting about that. Thank you, Astro Lover. I need to pick some problems for that. I wrote a note to myself to do that over the weekend, and then I washed my hands and I lost it. I need to write a note somewhere on paper, if I can find a pen. Okay, I'm going to go ahead and stop the recording here then. Hope you all have a nice day.